I guess I'll just go ahead and introduce Dr. Williams.
Since I knew my predecessors would be given overviews in their presentations, I have chosen to give a very focused presentation. The title of my talk is called Civilizing Coal, and my presentation represents one of the major fruits of more than a decade of collaboration between my Energy Systems Analysis group at Princeton and a colleague of Professor Ches at Tsinghua University, Professor Li Zheng. And what I am going to do is give a very focused presentation of polygeneration, which is a major aspect that Professor Xu presented in his introductory remarks here, and has been a major focus of our collaboration with Tsinghua over the last decade. And I'm going to be very narrowly focused on economics for this one particular case. And I'm going to be talking about polygeneration as a strategy for simultaneously dealing with the carbon challenges, the health and ecosystem damages challenges caused by coal, and also looking at the major opportunities that have been alluded to by both of my predecessors, that you can also use coal to make synthetic liquid fuels. And the approach that I'm going to take here is to show how you can use polygeneration to realize deep reductions in greenhouse gas emissions, both for electricity and synthetic fuels, very cost effectively by combining gasification-based energy conversion, pursuit of CCS, co-processing of biomass with coal, and the co-production of synthetic fuels, electricity, and CO2. And with this strategy, you can also achieve these tremendous reductions in air pollution emissions and simultaneously enhanced energy supply security by the means of this strategy. And what I'd like to argue here is that technologically and economically, it is easier to mitigate climate change, air pollution, and energy security simultaneously than it is to do these things separately, which seems counterintuitive, but it arises because of a lot of the synergisms in these systems. So I'm going to skip over some of the slides because of what my predecessors have already said here, and I'm going to say something briefly about a couple of the major options that have already been highlighted. One is post-combustion CO2 capture, and I'd like to point out that this is probably the simplest way forward for doing carbon capture and storage for coal-fired power generation, in that it's the least disruptive approach from the status quo, but it's very energy intensive, very water intensive, and very costly. My predecessors have also talked about gasification-based strategies, and in particular, coal IGCC technology. This has the big advantage over post-combustion capture in that it involves pre-combustion capture that requires much less energy penalty than is required with post-combustion capture. But one of the fundamental problems that has challenged IGCC technology is that if you're not going to do CCS, the power plants that just vent CO2 are less economically efficient than conventional pulverized coal power plants. So I'm going to be focusing here on co-production of synthetic liquid fuels, and for specificity, I'm going to be talking about Fischer-Tropsch liquids with once-through system configurations, where you pass the synthesis gas from the gasifier through the synthesis reactor, and you use the unconverted synthesis gas to make electricity in a gas turbine, steam turbine combined cycle. And this is just a configuration of how these systems look, what these systems look like, and typically in these systems, about 2/3 of the energy output is in the form of liquid fuels and 1/3 is in the form of electricity. And I'm going to be talking about coal-only systems and coal plus biomass systems. And for the coal plus biomass systems, I'm going to distinguish between two different cases. One is what you can do during this decade with modest amounts of biomass as a feedstock, less than 10%, say. And if you're going to use less than 10% biomass, you probably are going to choose to gasify the biomass and the coal in a single gasifier. But if this technology is successfully launched in the market, it's very likely that in the longer term, post-2020, we would not be doing it that way. We would be having separate gasifiers for coal and biomass. So why does one want to think about co-production systems as power generators? And that's what I'm going to focus on here, is looking at these co-production systems as power generators. First of all, there's a major energy efficiency gain relative to producing fuels and electricity in separate facilities. And then second, a very important aspect of these systems is that the cost of CO2 capture is much less for these co-production systems than it is for standalone power plants. And the reason for that is whenever you make liquid fuels, synthetic liquid fuels from coal-derived syngas, you have to remove the CO2 that's generated upstream of synthesis before it is put into the synthesis reactor, whether you're worried about the climate problem or not. And so it's very cheap to just compress that, capture that CO2 and compress it and put it underground somewhere. And the third thing that is really important is that these systems just shine incredibly in the world of high oil prices, because you get a large credit for the sale of the liquid fuel co-products, which drives down the generation cost of the assigned to electricity. So why do you want to co-process biomass? In these systems, and the ones that I'm going to highlight here, put about 65% of the carbon in the feedstock underground. Okay, about 25% ends up in the synthetic liquid fuels. And when you put CO2 underground that is derived from biomass, that is negative greenhouse gas emissions, because all the CO2 from the biomass was extracted from the atmosphere during photosynthesis. And those negative emissions can be used to offset the positive emissions from the coal-derived synfuels and also the positive emissions from coal-derived carbon at the conversion plant. And the economic benefits that are provided is this enables you to exploit the economies of scale for coal energy conversion, the lower average feedstock cost compared to biomass-only systems, because biomass is typically much more expensive delivered to the plant than coal is. And also the levelized cost of electricity declines sharply with greenhouse gas emission price at high biomass co-processing rates. And a very important strategic benefit of this is it enables the exploitation of coal to make low-carbon transportation fuels. And an important metric that I'm going to introduce here is what I call the greenhouse gas emissions index, which I define as the total greenhouse gas emissions for production and consumption for the system that I'm describing, divided that by the total greenhouse gas emissions for consumption or production and consumption of the fossil energy displaced. And for the purposes of this analysis, I'm going to assume that the fossil energy displaced is the equivalent crude oil-derived products and electricity from a new supercritical coal-fired power plant that vents CO2. And these are the 8 systems that I'm going to focus on. The top 2 are a pulverized coal plant that vents CO2, one with CCS, with post-combustion capture, an IGCC plant with pre-combustion capture, and then 4 co-production systems. CTLE means coal to liquids and electricity. Okay, CBTLE means coal and biomass to liquids and electricity, and the percentages there are the percentages of biomass that you're including in the system. So I'm going to look at something for this decade, which is 5% biomass, and then one for the longer term, which is 29% biomass. And notice that if you have one of these co-production systems that is based only on coal with CCS, you get a 30% reduction in the greenhouse gas emissions. In other words, a GHGI of 0.7. If you have 5% biomass, the greenhouse gas emissions index is 0.5, and if you have 29% biomass, it's less than 0.1. In other words, more than a 90% reduction in emissions. I'm also going to make a comparison to nuclear plants in this, and I should point out that all of my analysis is not for first-of-a-kind plants, it's for nth plants, and these are for U.S. conditions, and we have not yet worked out the economics for Chinese conditions. We hope to be doing that during the course of the next year. This graph here is very, very complicated, but I want to spend a couple of minutes on it because it's very important. This is the levelized cost of electricity in dollars per megawatt hour for these different systems that I just described to you as a function of the greenhouse gas emission price going from $0 to $100 a ton of CO2 equivalent. Now, we're over on the left-hand side of that graph here with $0 a ton in both of our countries because we don't have carbon policies at the present time. What I want to call your attention to is several things associated with this graph. First of all, the dashed lines here represent fossil energy systems that vent CO2. The solid black line is a supercritical coal plant that vents CO2. The dashed gray line is a coal only to liquids and electricity plant that vents the CO2. And the solid gray, the red, and the green lines are all co-production plants with CCS for coal only, 5% biomass, and 29% biomass respectively. Near the top of the graph, what you see is the solid black line is the levelized cost of electricity for a post-combustion capture system for the pulverized coal plant. And I want to point out to you that where the solid black line and the dotted black line cross represents the greenhouse gas emission price that's needed to induce by market forces carbon capture and storage. And you can see that's extraordinarily high. It's like $70 a ton. Okay, notice the solid blue line, that's the IGCC with the pre-combustion capture, and the crossover point there is a lot less. It's about $56 a ton instead of $70 a ton. So it's a lot better, but the costs are still extraordinarily high compared to the present time. And in fact, if you look at that crossover point with the blue line, it represents an increase of 70% in the levelized cost of electricity compared to an existing coal plant that vents CO2 at zero carbon price. So those are very big penalties. But look how much lower the costs are for the co-production systems, even at very modest greenhouse gas emission prices. And in fact, at zero carbon price, both the coal only and the 5% biomass plant are much cheaper provide much cheaper electricity than does the pulverized coal plant that vents CO2. And why does this happen? Because this is evaluated here at the current oil price, which is about $100 a barrel. So you get this enormous benefit from those coal products. And for those of you who aren't used to thinking about dollars per barrel, this $100 a barrel corresponds to more than $700 a ton of oil, which is, I think, the units that our Chinese colleagues are much more familiar with. But if you deploy a lot of these plants, the world oil price is not likely to stay up at $100 a barrel. It's going to go down, okay? And so a very important metric that you want to think about here is what is the break-even crude oil price? The lower the better, okay? You want the break-even crude oil price is the price at which the synthetic fuels would be competitive with the crude oil products being displaced. And I want to call your attention to the fact that the green line there, now remember that represents a system with more than 90% reduction in greenhouse gas emissions, crosses the least cost line that's the gray line there, which is coal only, at about $55 a ton of CO2, which is the minimum market price for IGCC coming into the market with CCS systems. And at that price, the break-even crude oil price is not $100 a barrel, it's $60 a barrel, okay? And if you push this further to carbon prices that would enable post-combustion to come into the market, you can see that you can drive the prices down to even lower than that. And if you think about decarbonizing natural gas combined cycles, they require a carbon price more than $90 a ton, okay? And at $90 a ton, you can see the break-even crude oil price is $30 a barrel. We're not going to go back to $30 a barrel in the future, regardless of how much of this we put in the system. So the message of this is that a good way to protect against the risk of oil price collapse is to have a very strong carbon mitigation policy combined with a high rate of biomass co-processing. They give you a high degree of risk against the risk of oil price collapse. But how are we going to get started? We don't have a carbon mitigation policy at the present time, so what can we do? And our thinking at the present time is that you want to do two things if you want to move this technology forward. First of all, initially exploit the opportunities for enhanced oil recovery that my colleagues have already mentioned here. This is a very well-established technology in the United States, And I think that there are probably significant opportunities in China, but they're much more uncertain than the opportunities in the United States. And of course, as I've already indicated, we want to process just a small amount of biomass for these first plants. And I'm going to point out that in the United States, I'm not going to go through all the numbers on this slide, but I just want to point out that the CO2 EOR resource, the technical resource, is probably comparable to what we can get from new oil on the outer continental shelf in the United States. Okay, and this is much easier in many ways to exploit than new oil on the outer continental shelf, and much less controversial. And I want to point out that these systems have a very attractive approach to CO2 EOR. And that is, you don't have to be nearby in order to exploit the CO2 EOR opportunities. And that's because the costs of CO2 capture are extremely low for these plants. And I'm considering these plants with 5% biomass with a selling price of CO2 at the plant gate that brings the levelized cost of electricity down to the level of a coal-only plant that vents CO2. Okay, and that turns out to be an extraordinarily low $6 a ton for these plants. And what I've suggested here is you might have a cluster of these plants that are remote, a long distance away from a CO2 EOR site. And I suggested that say 5 of these plants combine their CO2 streams into a long trunk line that would carry almost 40 million tons a year of CO2 to a distant CO2 EOR site. And you can see that I've shown the calculation here, what the cost of delivered CO2 would be. It would be like $20 to $30 a ton, which is less than the market price for CO2 EOR in the United States. Okay, and this graph here shows what those levelized costs again. If all the systems in here sell CO2 for at the plant gate for $6 a ton, and you can see that all of the co-production systems in this case, even the 29% biomass case, are less costly than a coal plant that vents CO2 at $0 a ton carbon price. So you don't need a carbon price to get started with this. You don't need nearby CO2 opportunities, CO2 EOR opportunities to get started with this, but you do need a pipeline infrastructure, and you got to build that, okay? So now I'm going to ask the question, is China likely to be an early mover with CCS technologies? First, I want to point out that despite the attractive economics and environmental benefits of these systems, they face formidable institutional obstacles. First of all, the technologies require managing 3 products simultaneously that serve radically different commodity markets. Those are liquid fuels, electricity, and CO2. And you have to ask this question, who's going to own and operate these plants? It's not a comfortable fit for having coal companies or power companies and oil companies in joint ventures with one another because they're culturally very different. Coal companies are logical candidates, but most coal companies in the world will not be comfortable with energy conversion technology, especially gasification-based energy conversion technology, but that's not true in China. And the reason for that is that various coal companies in China have extensive experience with energy conversion, including gasification. And this is a map from a paper that also came out of our Tsinghua collaboration showing early CCS opportunities in China. And each of those 400 pins represents chemical plants that involve coal gasification in China. These are plants that are either existing, under construction, or on order. Okay, and we identified more of the order of 20 of these plants that co-process more than 1 million tons a year that would be near prospective CO2 storage projects and very good potential candidates for some of these early action activities. So I'm going to show you now a thought experiment for China of the implications of this. And I'm going to imagine that all new power plants in China that are built between 2016 and 2035 are not supercritical PC plants, but instead are either IGCC plants with CCS, CTLE plants with CCS, or the CBTLE plants with biomass. And I'm also going to add in nuclear power and ask the question, what are the implications for each of these options in turn with regard to greenhouse gas emissions and oil imports? And this is sort of the business as usual trajectory for greenhouse gas emissions for China, and oil imports and coal electricity involving about a doubling of CO2 emissions in this period. And this is the results on greenhouse gas emissions for in the period to 2030. And you can see here that relative to business as usual, the two lowest curves that represent both the BTLE, CCS, 5% biomass, and nuclear power reduce greenhouse gas emissions by about 2.3 billion tons per year. Okay, that's very surprising result since the GHGI value of nuclear is 0 and the GHGI value of the 5% biomass is 0.5. But you've got two products with the CBTLE plant, and you're decarbonizing each of them by 50%, and they're about the same emissions reduction. So you get the same emissions reduction as you would with nuclear power. But if you did that with nuclear power, the amount of extra nuclear power China would have to build between now and 2030 is comparable to the total world nuclear power capacity at the present time. As far as oil imports are concerned, they would essentially vanish for both of these co-production options. And so, in fact, with the 5% biomass case, you would actually become a mild exporter in this period. So I'm going to suggest that a U.S.-China collaboration to launch these technologies in the market might be of great interest. And the collaboration might be based on first-of-a-kind commercial-scale demonstration projects in EOR applications. There should be perhaps a demonstration project in each country that would go along with collaboration on ancillary R&D and a collaboration on overcoming the formidable institutional obstacles to these plants. And to this collaboration, the U.S. would bring extensive CO2 EOR experience and some experience with IGCC technology. China would bring extensive experience with chemicals manufacturing via gasification and some experience with gasification-based synfuels production. This collaboration would help establish the robustness of these technologies in the market and bring the plant performance and cost information into the public domain so that the technology can be readily scoped and financed by a variety of industrial players. Thank you.
All right, thank you, Doctor. We're